Okay, welcome to one of my favorite assignments. I love doing these problems. Okay, so the deal here is we want to try to figure out what the heat of reaction is for each of these reactions, and based on that we're going to decide if it's endothermic or exothermic. Now the first step is you have to balance the chemical equation because you have to know how many moles of each reactant and product are involved in order to figure out how much energy it takes to disassemble and reassemble them. So let's get started. I'm going to balance this chemical reaction right now. So let's see. I believe what I need to do is it balances out to have a 2. I'm cheating. I've already done this. 2 and 2. Alright, that's the first step. Balance the chemical equation. The next step is you have to look and say, alright, how much energy does it take to break apart the reactants? I have to add that energy. So it's going to be positive. Now what I do is I look at my heat of formation table and I see sodium is an element. It's not a compound, and the heat of formation for an element is always going to be 0. So I have 0, well 2 times 0, plus, now what I do is I look up H2O liquid on my heat of formation table, and when I do, I see that H2O liquid is negative 286. So this is negative 286 times 2 because I have 2 moles of it. But the thing is, I'm going to put this in parentheses here since I want to add it. Now the thing is, on this side, the heat of formation tables are saying this is how much heat energy is released when you form something. So if I was to form 1 mole of water, it would release 286 kilojoules in forming that 1 mole. But I'm not forming this one. I'm actually breaking it apart so I can reassemble it over here. So what you want to do is, on this side of the arrow, on the reactant side, you always want to take the heat of formations, which are always listed as negative, and make them positive. Because what we're going to do is we're going to add the energy, not take it apart. So now what I do is I say, alright, 2 times 286. I'm not even going to worry about what that is right now. I'm going to go to the other side of the arrow. On the other side of the arrow, I'm going to leave things negative over here because I am going to, once I disassemble these particles, I'm going to reassemble them as these, and heat energy is going to be released. So I have 2 moles here, so I'm going to say 2 times, and in this case, let me just make a time sign. I'm going to leave it negative because it really is forming. It is releasing that energy. So I look up sodium hydroxide, NaOH, and I see it's negative 470. All right, and now here I say plus negative, well, it's 0, so I can ignore that. So all I have to do now is multiply this right here. And when I do, what I'm going to get is 5, this is 572, and then I multiply this, and when I do that, what I get is negative 940. So then I just say 572 minus 940, and you know what I get? I get negative 368. That means, the way I interpret that is, this reaction will release or get rid of 368 kilojoules of energy. Since it's getting rid of it, that makes it exothermic. So let me just go ahead and circle it. It is exothermic. And that means this is a reaction that is actually going to happen, that nature wants it to happen because nature wants things to release energy. So let's just get going. I'll try to do a little bit less explanation now. Alright, I'm going to balance number 2. You know, I'm going to try to make it a little bit bigger if I can. How does that look? No, I can't see it. Alright, there we go. Alright, so here's what I'm going to do now. Let's see, I'm going to cheat. I'm going to look at, I've already balanced it. So the AgNO3, that takes, whoops, that takes a 2. And then 1 PB, 1 PbNO3, and 2 Ags. So now that I've got it balanced, I want to figure out how much energy does it take to break apart the reactants. So I'm going to look up silver nitrate on my heat of formation table, And when I look up silver nitrate, I see negative 101, but I'm going to make that positive 101 because I'm breaking apart, and I'm going to multiply it by 2 because there are 2 moles of it. Now lead is 0, so I'm going to ignore that. So 101 times 2, that equals 202. I'll write that in red. 202 is how much energy has to be put in to break apart the silver nitrate. Now I want to see how much energy is released over here. This is going to release 0. It doesn't take any energy to form silver, but I'm making 1 mole of lead nitrate. So I look up lead nitrate. Lead nitrate is negative 416. So what I do is I say 202 minus 416. And when I do that, what I'll get is negative 214. So I'll write in negative 214. And that is negative, meaning it's releasing energy, which means it is also an exothermic reaction. Let's try number 3 here. Number 3, and move this a little sideways a little bit. Number 3. Let's see what we got. Okay. For number 3, I've got to balance this. You know what? This is already balanced. That's cheap. Okay, you didn't have to do that work. So now what I do is I say, well, how much energy does it take to break apart copper? None. 0. It's an element. But how much energy does it take to break apart 1 mole of zinc nitrate? Zinc nitrate, it looks like it says the heat of formation is negative 586, but I'm going to make that positive 586 because I'm not forming it, I am unforming it. I'm breaking it apart. So it had a negative sign. It had a negative sign in the heat of formation table. I took that off because I'm not forming, I'm breaking it apart. Now on this side over here, I'm going to leave it negative because I am forming the copper nitrate. Now copper nitrate, here it is, it's negative 350. So I'm going to say, in my calculator, 586 minus 350, there goes my telephone. And of course it was a telephone solicitor, but at least it was from an organization I like. Okay, now, so this, let me show this again. So we're going to say 586 minus 350, and when we do that, what we get in this case is not negative, but we get positive 218. The fact that this is a positive number means that this reaction would only happen if we were to add, I'm just going to write a positive sign, if we were to add 218 kilojoules. And that means it is an endothermic reaction. It would only happen if you put energy into it. And because it's endothermic, it is very unlikely to happen. Nature doesn't really want to have these endothermic reactions. Where is this energy coming from? Huh? Let's try number 4. I'm going to balance it. Let's see, number 4 is, I've got a 2 in front of the HCl. And do I have anything else? No, I think that's balanced. Alright, so that means I have to break apart 1 mole of zinc. Done. 0 energy needed. I have to break apart 2 moles of HCl. So let's see what HCl is. HCl's heat of formation is negative 167, but I'm going to make it positive 167, so 167, and I have to multiply it by 2 because I have 2 moles of it. So that's how much energy has to be added to break apart the reactants. When I multiply that through, what I get is 167 times 2, that's 334. I'm going to write that in red. 334 kilojoules have to be added to break it apart. Now what I'm going to do is I'm going to subtract whatever energy is released in forming 1 mole of zinc chloride and 1 mole of hydrogen. Well, this is an element, so it releases 0 kilojoules. But let's look up zinc chloride. Zinc chloride is negative 488. And I'm not going to multiply because there's only 1 mole of it. So if I say 334 minus 488, you know what I get? I get negative, whoops, here's what I get. I get a problem here. I get negative 154. Since it is a negative sign here, that means it is an exothermic reaction, and it's one that nature will allow. Let's keep going here. Let's see what we got. Let's keep going here. Alright. Let's balance this one here. What are we dealing with? This is number 5. Okay, we're going to balance number 5 here. Number 5. Ooh, boy, this is a nasty one. Just trust me on this. When you balance it, here's what you get. You get 11 of these, and you get 12 of these. Gotta love these hydrocarbon combustion reactions. And you get 12 of these. Okay, here we go. In order to make this reaction happen, here's what I'm going to have to do. I find the heat of formation of H2O liquid. Liquid H2O is negative 286, but I'm going to make it positive 286. So 286. I have to add 286 joules for every mole, and guess what? I have got 11 moles. So I'm going to multiply that by 11. Yeesh. And I'm going to add an additional amount of energy, because now what I have to do is I have to break apart carbon dioxide as a gas. So CO2 gas is negative 393, but I'm going to make it positive 393 because I'm not forming it, I'm breaking it apart, and that's per mole, and I have 12 moles. Man, does it take a lot of energy to break up 11 moles of water and 12 moles of carbon dioxide. And then when I do it, I'm going to form 1 mole of this and 12 moles of this. Well, guess what? That doesn't release any energy because it's an element. So then I just look at what this is. Let's see, C12. Man, where's that? Here it is, C12H22. I think that might be like sucrose or something weird like that. That is negative 2, 2, 2, 1. So what I'm going to do is I'm going to go ahead and I'm going to multiply 286 by 11, and then I'm going to add it to the product of 393 times 12, and then I'm going to take away 221. And when I do that, what I end up getting is a rather large positive number. The number is positive, so I write a plus sign. That's a terrible plus sign. That's even a worse plus sign. I wonder if I just erase what I just did. No, that didn't work. Darn it. Alright, hang on. Eric. Alright, so I guess I can't erase it. This is really bothering me. Alright, well, let's consider that to be a plus sign. Alright, it's 5,641. So 5,641 kilojoules have to be added. And that means it is very much an endothermic reaction. And it is not about to happen on its own. Now, interesting, photosynthesis, that's how it happens. Alright, but let's just go ahead and look at the next one. Alright, Al. Okay, this is going to balance out as I need 2 ALs. I need 3 I's. And I'm going to need 2 AlI3s. So, well, guess what? It takes 0 joules to break apart the aluminum because it's an element. And look, it also takes 0 joules to break apart the iodine. So, you know what? I know for a fact that this type of synthesis reaction is going to be exothermic. Synthesis reactions are exothermic, and that's why. So I'm going to form 2 moles of AlI3. So I'm going to look up AlI3. I'm going to let it stay negative. Negative aluminum iodide is 303. And I have to multiply it by 2 because I'm producing 2 moles of it. So this reaction is going to release 606 kilojoules. And since this sign here is negative, that tells me that this is an exothermic reaction. It's going to get rid of energy and send it into the environment. Let's look at number 7. When I balance number 7, I'm going to get a 2 here in front of the iron and a 2 over here in front of the aluminum. And then I'm done. Now, if you remember, this is the famous, well, actually, this is not the famous thermite. This is the opposite of the famous thermite. So I bet you this is going to be endothermic. Let's just see. It doesn't take any energy to break apart the iron, but it's going to take some energy to break apart the aluminum oxide. How much energy is it going to take? It's going to take quite a bit. I'm going to have to add 1,675 kilojoules just to break apart that aluminum. Now when I do it, I'm going to release all of this energy, 0, because it's an element, and I'm going to release the energy of iron oxide. So when I find iron oxide is negative 842. Negative 842. So then I take my calculator and I say 1657 minus 852. So in other words, I added this much energy to break apart the aluminum, and I released this much energy when I formed the iron oxide. And so the net process was one that required a net input. I have to add 833 kilojoules to make it happen. And when you're adding energy to something, that is an endothermic process, and nature does not want it to happen. Okay, ever onward. Let's do number 8. We got to balance it. It means we need 2 magnesiums, and then we need 2 MgOs. I'm not really talking how to do the balancing. I'm assuming you already know how to do that. Okay, so let's just walk our way through this again. All right. I have to add 0 joules to break apart 2 moles of magnesium. How many kilojoules of energy do I need to break apart 1 mole of carbon dioxide? And the answer is I will have to add 393 kilojoules. Now when I do that, I am going to release energy. So I put negative, and magnesium oxide is negative 601. But it turns out I'm having to I'm going to form 2 moles of it, so I'm going to multiply that value by 2. Now this one here I'm going to ignore because it's a 0. I could include it, but it's going to be a 0. So basically what I have to do is I'm going to say, well, you know what, let's go ahead. This is going to be negative 1202. So I'm going to say 393 minus 1202. And when I do that, I'm going to get negative 809. And that means that it is, since it's giving off energy by virtue of having a negative sign, it is an exothermic reaction. Let's try number 9. Number 9 balances out. We did this one in class. This is the decomposition of hydrogen peroxide. As I recall, it was fairly exothermic and made a lot of steam. So when we balance this one here, we're going to get 2 moles of H2O2 is going to produce 2 moles of water and 1 mole of oxygen. So now I look up H2O2. H2O2, where are you? Alright, and it turns out the heat of formation is negative 191, but instead what I have to do is I'm going to make it positive 191 since I'm breaking apart and not forming it. And I have to double it because I have 2 moles of it, not 1 mole of it. And then I am going to form 2 moles of H2O. So H2O, I should learn this by now, is negative 286. And that's per mole. There's 2 moles of it, so I multiply it by 2. And I can ignore this because it's an element, and elements always have a heat of formation of 0. So I'm going to multiply 191 times 2, and then I'm going to take away what I get here. And when I do that, what I get is negative 190. And because this is negative, it is an exothermic reaction. The next one is the combustion of gasoline. You know that one's going to be exothermic, but there's something in this that's rather startling about this. So if you recall, this is a rather tedious one to balance. It works out to be 225. The carbon dioxide is 16, and this is 18. So I have to break apart 2 moles of this. So I'm going to say 2 times the heat of formation of C8H18. And that turns out to be C8H18 is 209. 209. And now I could ignore this one here because it's a it's a gas. So, I'm just going to do this in my head. 2 times 209, isn't that 418? I think it is. So I'm just going to write this as 418. You have to add 418 kilojoules to break apart 2 moles of octane. And when you do, you're going to release all this energy over here. Let's just see how much energy that is. Well, it's going to be whatever carbon dioxide is. That's negative 393. But that's per mole, and I have 16 moles. And then I also have 18 waters, and water, when it forms, let's see what we have here. It's a liquid, I'm saying, okay? So, therefore, H2O liquid is negative 286 times 18 moles. Good Lord. So I'm going to say 486 minus all of this, minus all of that. Because these are negative values. And when I put all that together, what I end up getting is negative, are you ready for this? 11,018 kilojoules. My friends, that is very much an exothermic reaction. It makes our cars go. It's amazing and powerful. In fact, we're about to find out just how powerful it is. But first, we're going to do this next one with KNO3. So KNO3, it's let's see, we put a 2 here, and we put a 2 here. So what I have to do is I have to, break apart 2 moles of potassium nitrate. So potassium nitrate, KNO3. KNO3 is negative 459, but I'm not forming it, so I'm going to make it positive 459. And I have 2 moles of it, so I'm going to multiply it by 2. Plus 0. All right, I'm not going to worry about that. And then over here, I'm going to, you know what, let's just see what that is. So if we say, all right, come on now. Come on, calculator. Turn on. Okay. So we're going to say 459 times 2. That's 918. I'll do it in red again. That's 918. And then copper nitrate. I'm forming 1 mole of copper nitrate. Copper nitrate is negative 350. So if I say 918 minus 350, what I end up getting is positive 568. Positive 568. That means it would only happen if you added 568 kilojoules, making it an endothermic reaction, and one that is very unlikely to happen. We'll continue on. Okay, so we only have 2 more? Okay, that's great. The detonation of nitroglycerin, which, by the way, I so generously balanced for you. Alright, it's already balanced, so let's just see what I have to do here. I'm going to have to take nitroglycerin, which is, let's see, CH, here it is, okay, yeah, that's the one, okay, and look, it doesn't have a very big heat of formation, negative 370, but I have to make that a positive 370, because I'm not forming it, I'm breaking it apart, and I multiply it by how many moles I have. Now over here I have 6 moles of nitrogen. It's an element, so it doesn't release any energy. 12 moles of carbon dioxide, so carbon dioxide is negative 393. I'm going to leave it as negative. So I have negative 393 times 12 moles. And then I have over here I have H2O again with H2O, that's negative 286. I'm going to leave it negative because I am forming it. And I have 10 moles of it. And then I can ignore the oxygen because it's an element. So when I multiply all of this through, and I'm going to take this positive value here, and I'm going to subtract this, and then subtract this because those are both negative. What I end up getting for the detonation of nitroglycerin is definitely an exothermic reaction. It's negative 6,096. what I find fascinating is that is basically half of what gasoline is. But the reason nitroglycerin is more powerful is because it happens more quickly. Alright, well, let's just do, we have a couple more to do. Let's just go ahead and blast our way through it. Oh, what, just one more? Okay. We only have one more of them, apparently. Okay, so what I have here is HCl. There's 2 of these. And then, that's all I have to do there. Just put a 2 there. Now, so let's see what I have to do here. I have to break apart 1 mole of calcium carbonate. Calcium carbonate is negative 1260, but I have to make that positive 1260 because I'm not forming it, I'm breaking it up. And then I also have to take 2 moles of HCl. HCl is negative 167, but I'm going to make it positive 167 because I'm not forming it, I'm breaking up. And I have 2 moles of it. So therefore, I'm going to have to multiply this by 2. And let's see what I end up forming. I end up forming 1 mole of calcium chloride, so minus calcium chloride is 876. And then I have water, which is negative, is that 286? Did I memorize it finally? Yep, it's negative 286. And I have carbon dioxide, negative, isn't it 4 something? Carbon dioxide, no, negative 393. Darn it. Hey, let's just figure this out. So I have 2 positive numbers. I have this one here, and I have whatever this equals, and then I have 3 negative numbers. And when I combine all of them, what do I come up with? It's a close thing, but it's barely negative. Negative 15 kilojoules. It is negative, so that means it is exothermic, and therefore nature wants it to happen. Now look at my answer here. It looks like there's 1 more on here, but darn if I see it on this sheet here. So, oh well. I enjoyed it. I hope you did too.